Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to part two of refraction in lenses. And today we are going to talk about a few things, mainly what causes light to bend and what determines the type of image formed by a lens. Okay, so we're going to start by talking about this paragraph here, and it's talking about Sir Isaac Newton. Isaac Newton was a famous scientist, and he was famous for a lot of things. One of the things he was famous for was separating white light. And so, in one of his famous experiments, he got a glass prism and he shone some white light on it from one side. And what happened was it separated into 7 different beams. Well, actually, we can't really quantify them as 7, but we do that anyway. So, what happened was it went from red all the way up to violet, and what we know as the rainbow. And anything below red is known as infrared, okay, because that means below red. And anything above violet is known as ultraviolet. We can't see ultraviolet, we can't see infrared because it's beyond what we can see. This is what we call the visible light. Visible means the stuff we can see. Visible, seeable, things we can see. So the visible light is from red, orange, yellow, green, blue, purple, violet. Did I miss any colors? Anyway, and every color in between. So that's basically the visible light, all the colors that we can see. The things that we can't see is infrared, anything below red, and ultraviolet, anything above violet. Some animals can see those, but we can't see them. Okay? Subhanallah. Right, let's look at the question here. Now, why did that happen? Why did light separate into those different colors? Before we start answering the question. Well, the reason it separated into different colors was because it had those different colors to begin with. So light is actually a mixture of those different colors. Okay? So, and the reason why it separated into different colors was because we started off with a mixture. As that light mixture comes in, all those different frequencies are there, and they separate into the different colors based on their frequencies, because light slows down and those frequencies bend at different angles, and so we get those different colors. Let's look at the questions. How did Newton prove that sunlight consists of many colors? He passed light through a prism. That's what he did. So we're going to write that in. He passed light through a glass prism. That's what he did. Describe a discovery that you made through your experimentation. Well, basically anything that you've done. I've done quite a lot. How about last week when we were in the lab and we were making those lenses? We discovered quite a lot, didn't we? We discovered that the curvature of the lens determines, or the mirror, because we made some mirrors, didn't we? So the curvature of the mirror, whether it's a convex mirror or a concave mirror, changes the focal point. And so if it's really curved, then you see a much wider angle lens than if it was flatter. And anything else that you might have discovered. I think one of my students told me that if you put eggs in vinegar, then the shell actually disappears. Well, that's true as well because the shell is high in calcium. And if you put, or calcium carbonate, and if you put it in vinegar, which is acetic acid, that forms acetic carbonate, calcium acetate, sorry, and carbon dioxide. So yeah, so there's a lot that you can discover with science, obviously. Right, moving on. Next slide. What causes light rays to bend? Well, that's a very interesting question. What causes light rays to bend? Let's read through this and then we're going to attempt to answer it. A fish tank can play tricks on your eyes. If you look through the top, if you look through the side of a fish tank, a fish seems closer than if you look at it from the top. If you look through the corner of the tank, you may see the same fish twice. Look at figure 1, for example. You see one image of the fish through the front of the tank and another image through the side. The two things appear in different places. How can this happen? How can a fish appear over here and appear over here, but it's the same fish? Well, it's due to something called refraction, which is light bending. You see one image through the front and one image through the side because of refraction. Refraction, this word here, and I would like you to highlight that, please. So let's bring our highlighter along, and yellow is fine. Refraction can cause you to see something that is not actually there. How does it do that? You look at the fish in the tank, the light coming from the fish to your eyes bends as it passes through three different mediums. Three different mediums. What's a medium? A medium is something like air, water, a vacuum, glass, plastic, diamonds. So all those transparent mediums, they allow light to pass through, right? But they're all different. Okay, so we have some of those are gases, some of those are liquid, and some of those are solids. So air, for example, is primarily gases, obviously. Then we've got liquids like water, and then we've got solids like diamonds and glass. So each of those is a different medium. And what happens to light is as it goes from one medium to another, it depends on the medium. It either slows down or speeds up. So think about you, for example. I would like to think of yourself as a beam of light. If you're going through vacuum, if you're going through the vacuum of space, you're traveling as fast as you can go. So that's when you're traveling at the speed of about 300,000 kilometers per second. Yes, that fast. Okay, so then what happens if you suddenly go into a medium that has more density of particles? So we went from a medium with no particles whatsoever, and that's outer space, to suddenly, now you're flying through as a beam of light, and suddenly you've got air. So you're going through air. So you're going to obviously feel a bit of air resistance. You're going to slow down slightly. And that's what happens to light. So as light goes through the air, it slows down and it bends. Okay, so what happens if it goes through water? What would happen to you if you go through water? You're going to slow down once again because the density of the particles, how close the particles are to each other, is much more now. And then I want you to imagine going through sand, maybe. Okay, now that's going to be really hard because obviously the particles are really, really close to each other in a solid. And so that's precisely what happens. So when light goes through from a medium of, say, air into water, it bends, the light bends. Now, I'm going to attempt to explain this in the simplest way possible, but I don't want you to worry about why it bends at this stage. So all you're required to know is that it bends. But in case you're interested, I'm going to try and explain it briefly. So here is light. So we're going to try and use this highlighter. Okay, so here is a ray of light. Okay, and it's traveling this way. Okay, it's traveling this way. And there it is, just happily traveling in more or less a straight line. Now what happens next, I want you to pay attention please, is that this happens. So it's going from one medium to another. So let's say for example, this is air and this is water. Okay, this is air and this is water. So as light comes through, and I'm going to go back to using my highlighter, as light comes through here, as you can see, this part of light, this part here, okay, that part has already hit the water, so it's slowing down. And now, but this part is still traveling fast, okay? So we're talking about one beam of light here, so this is a very, very thin line. This whole thing, that's a very, very thin line. But this part of it, the inside part, has hit the water, which means it's slowing down now, and the outside part is still going quickly. So what happens is this is going slow and that's going fast, and so it immediately starts turning. Okay, so it starts turning ever so slowly. So that's actually what happens is it pivots. That's a word from physics. So it pivots, and then we get an angle, and that's why it looks like it bends as it goes from one medium to the next. Okay, so it pivots when it goes from one medium to the next. But of course, it happens also the other way around. So it goes from water to air, then it bends the other way. So it depends on which way it's going. If it's going from air to water, it's going from fast to slow. It's going to bend inwards towards the normal, what we call the normal. Now, what is the normal? The normal is this perpendicular line that runs across the surface. So it's at 90 degrees to the surface. And if the beam is coming in like that, okay, then it hits and then it bends towards the normal. So that means this angle over here, let's say for example that's 40, oh, it's a bit more than that. Let's say for example that's about 60 degrees, then this angle here is going to be about 30 degrees and so on. Depends on the reflective index. And we're going to come to explain what that means. So all I want you to know here is that light bends when it goes from one medium to another. And I want you to remember a medium can be, what are some examples of mediums? A medium can be air, vacuum, water, clear plastic, quartz, diamonds, alcohol, oil. So anything transparent really can be a medium. Okay? And what else do we have here? So basically, let's continue reading. As light passes from one medium to the next, it's refracted. So the word refracted simply means bends. Okay, so it's just a scientific word that means bends. So refraction of light just means bending of light. When light rays enter a new medium at an angle, the change in speed causes rays to bend. Okay, that's all you need to know here, is that light will bend when it goes from one medium to the next. Depending on whether it's going fast to slow or slow to fast, it will bend either inwards or outwards. Okay. We do have a question here. The question says, discuss with classmates some other examples of how the appearance of objects in water is different than in the air. Describe these examples below. So you might say, for example, that objects in water look bigger and closer than they actually are. Sometimes an object will look crooked. Part of it is underwater. If part of it is underwater, especially, and then another part is above water, then it might look like it's chopped in half, and it might look a bit more crooked. So anything like that would be okay. But yeah, certainly I've noticed that sometimes objects in water look a bit wavy or look a bit bigger than they would if they were out of the water. And maybe the colors would be a bit more vibrant. I remember Uthman told me that. So yeah, that's something I've noticed as well. So if you take an apple and you put it underwater, the colors look slightly different, and that's got to do with the refraction as well. Okay, let's have a look at the next page here. So the next page talks about refraction in different mediums. And we've sort of covered that already slightly. And it's more or less the same concept, which is that light bends when it goes from an area of one medium or slow or fast to another medium where it's going to experience a difference in speed. So some medium cause light to bend more than others. Figure 2 shows how the path of light ray changes as it passes from one medium to another. When light passes from air to water, the light slows down. Light slows down again and bends even more when it passes from water into glass. And that's expected because obviously it's slowing down. So over here it's going and then it's bending and then it's bending once again. Oh, that's a horrible color. Let's change that. That's supposed to be highlighter. So we'll go with that. Yep. So bends, bends again, and bends again. But then, of course, if it goes from slow to fast, it bends outwards. Slow to fast, it bends outwards. Now that's very interesting. Okay. So I'm just going to make a note of that. And the reason I'm making a note of that will become apparent soon. Slow to fast, slow to fast, slow, fast. It bends outwards. It bends outwards. Interesting. Okay. What else do we know? What else do we know here? Notice that the ray that leaves the glass is traveling in the same direction as it was before it entered the water. Light travels fastest in the air, a little slower in the water, and then slowest in glass. In this example, glass causes light to bend even more than both air and water. Another way to say this is that glass has higher index of refraction. So that's the first time you're introduced to this word. Index of refraction. That's just a fancy word that means number of bending. Okay, so if we were to put a bending number, how much light bends or breaks, then that's what we're talking about here. So index of refraction just refers to how much the light is going to bend. Um, and so different materials, turns out, have different numbers that describe how much light is going to bend. So here we start with air, which is 1.00, but that's only because they're going to do decimal places. If they got three decimal places, it would be 1.003. And the true 1.00 would be a vacuum. Okay. And so it starts ever so slightly being slowed down in the air, and then in the water it slows down quite a bit compared to quartz, where now obviously it starts slowing down even more. And notice something here, obviously now we've got most of the solids down here, there's a solid here too. And then sort of kind of liquids in the middle, and then we've got gases up here, and of course a vacuum up here. Okay, let's have a look. So the index of refraction refers to, or refractive index refers to, refractive index is the number, okay, the number that indicates how much light bends in a certain medium. Okay, that's all it is. Just a bending number. Okay, let's have a look here. We've got some questions here to do. We've got some data analysis. Love those maths questions. Which medium causes the greatest change in the direction of light rays as it enters at an angle? Okay, which medium will cause the greatest change in the direction of a light ray that enters at an angle? So we're assuming here that it's going to enter from the air, and so it's going to be the one with the highest refractive index, so it's going to be diamonds. But of course, as you are reading the questions, you are making some assumptions, because obviously, if it's going from zirconia into diamonds, then it's going to bend quite a bit, but it's not going to be the same as, say, if it was going from the air into zirconia. So we're just going to assume that it's going from the air into whatever medium. Okay, question two. According to the table, which tends to bend light more, solids or liquids? Generally speaking, it's solids. Once again, I'm saying generally speaking because this is solid, 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 but then we have another solid up here. So generally speaking, it's solids, but some liquids are bending light more than solids, like corn oil and glycerol. Okay, predict. Now the last one is a really nice question. It says predict. Would you expect light to bend if it entered corn oil at an angle after it traveled through glycerol? Now that is a very nice question. Now what I'm going to do is I'm going to make some space over here because I think it's the kind of question that deserves a picture. And you guys know how much I like to doodle. So let's have a look. Put my artistic skills to the test. So here we have, I'm going to draw a cylinder. And here we go. These are the walls of the cylinder. And here's a bit of a shine to it. There you go. And we've got, you know what? I'm going to give it a wall as well on the inside. And I'm going to draw what looks like the inside barrier as well. Why? Because I can. That's why. Okay, here we go. So that's what the cylinder looks like. I'm going to fix that shine. That's what the cylinder looks like, right? Now, what it's saying is that it's got two liquids in there. So we've got corn oil and we've got glycerol, and light is traveling from one to the next. So let's draw these. So I've got corn oil and I'm going to put that, oh, sorry, I'm going to use my highlighter. I'm going to put that over here. Okay, so that's corn oil for you. That's corn oil for you, kind of yellowy in color. Okay, there we go. Now we've also got glycerol, and glycerol is over here. Okay, and that's what we have. So we have corn oil and we've got glycerol, and they are on top of each other. Now you can safely assume that the glycerol has a lower density, which is why it's on top of the corn oil. Let's have a look. And if I want it to be fancy, I can give it a bit of a lip here. This is also a bit of an art lesson. Why not? Give it a bit of a, that's the surface on top. Showing off now. Okay, let's draw the light beam. So we've got a light beam and I'm going to choose orange for the light beam. And I'm going to make sure that I use the right type of pen. Okay, so that should be fine. I've got the light beam and it's coming in through here. Oh, actually, that's not a very good color because I really want it to be distinct. Oh, I'll have that. So here we go. So that's light. It's coming in. It's coming in at this angle. Now what's going to happen is obviously it's going to bend. And remember, slow to fast bends outwards, outwards. So it's going fast to slow, so it's going to bend inwards. Okay, so that's going to go like that. Now the question's asking, go back to the question's asking, would you expect the light to bend if it entered corn oil after traveling through glycerol? Now this is glycerol. And this is corn oil. And so what would you expect to happen to the light ray? Well, look at the refractive index of glycerol, and that is 1.47. And what is the refractive index of corn oil? Well, it turns out it's exactly the same. It's 1.47. Therefore, since there's no difference in the refractive index, light's going to continue moving and it's going to completely forget to bend. It's not going to bend. Why? Because the speed of light isn't going to change. Since the speed of light isn't going to change, it's going to continue moving at the same angle, more or less, and therefore it's not going to bend in this instant. So that is going to continue going in a straight line. No bending is going to take place. Okay, so the answer is no, not going to bend because they are what the same they have because they have the same refractive index. Okay, let's look at the next page here. Ooh, that's lovely. Prisms and rainbows. Back to the rainbows. Recall that when white light enters a prism, what happens? Each wavelength is refracted by a different amount, which means each wavelength of light, each color, will be bent at a different angle. The longer the wavelength, the less the wave is bent by a prism. So red with the longest wavelength is refracted the least, while violet with the shortest wavelength is refracted the most. Okay, so that's quite interesting. Red is refracted the least, while violet is refracted the most. Okay. The difference in refraction causes white light to spread out into colors of the spectrum, which we know as the rainbow. Um, okay, very good. And just a very quick note on that, just sort of reminded myself. A lot of my students will say that's قوس قزح. That's not really something that you should be saying because قزح is one of the gods or so-called gods from Ayyam Jahiliyyah. So basically, back in the days of before Islam, there was an aliha called Quzah, and so people used to say when they say saw rainbow, they say that's Qaus, a bow, the bow of Quzah. And Prophet Muhammad والسلام, said, don't say Qaus Quzah and say Qawsullah. Okay, so yeah, so please do not say Qaus Quzah, say Qawsullah or Qaus al-Matar. Okay, so let's move on. The same process occurs in water droplets suspended in the air. When white light from the sun shines through the droplets, a rainbow may appear. The water droplets act like tiny prisms, refracting and reflecting the light and separating into the different colors. Okay, so let's have a look here. So we've got a diagram and we've got to answer some questions. We've got white light coming in. Let's just have a look at the diagram. I don't want to read the questions just yet. I just want to have a look. Just read it. Just look at it and sort of um, study it before even reading any of the questions. So we've got what looks like white light over here. Then we've got some rainbow colors. Some of them are getting reflected and then sort of twisted, and then they leave. Interesting. Now let's read the questions. Why does light separate out into its colors at point A? Well, that's quite easy. That is due to refraction. So what happens is light speed changes, causing refraction. Okay, so it's basically refraction, and different colors refract by different amounts. At point B, what happens to each color of light at point B? Um, what happens at each color of light at point B? Well, let's see. So obviously, we have reflection. Now, that's very interesting because I'm looking at that, and it's basically showing that it's all reflected internally. Um, Now we haven't actually talked about total internal reflection, but this is what this is showing. So it's showing all the lights being internally reflected, and this is something called total internal reflection. But we're not going to talk about that now. Basically, it happens when light is at the right angle. Like when you're pointing a laser pointer or a flashlight at a glass window, some of the light will obviously go through the glass window, but then some of it will be reflected away from the window. But if you point it at the right angle, you'll get more and more of the light reflected as opposed to going through. And this is what we're experiencing here, is that just the rainbow is just hitting at the right angle, so it's all internally reflected. So what I'm going to say here is that the rainbow, or that's, I shouldn't say that, the colors, okay, what's a good way of saying it? The different colors, I would say, the different colors, and we'll write it the American way, are being reflected. And that just means they are not being refracted. They are not going through and bending or breaking. Reflected. Yeah, they are just being reflected internally. What happens to each light ray? What happens to each color of light at point C? Now, at point C, that's something also very interesting. What happens at point C is that we have refraction once again, refraction again. But this time it's going from slow to fast. This time it speeds up. It speeds up and bends. And bends what? Do you remember what we said? We said slow to fast goes outwards, fast to slow bends inwards. So it's going slow to fast, so it's going to bend outwards. Okay, very good. Ooh, mirages. What is a mirage? So let's read through this quickly. When you're traveling, when you're traveling in a car on a hot day, and you notice that the road ahead looks wet, yet when you get there, the road is dry. Did the puddle dry up? No, the puddle was never there to begin with. What you saw was called a mirage. And that's something that people have talked about for years, actually. And here in the Middle East, obviously, because it's a desert, and especially here in Kuwait, you do see it. I've been out in the desert, especially sort of around noon or afternoon when it's really hot. Obviously, it has to happen in the morning because that's where when light is out. You need light, um, and that's when you notice a mirage. Why does a mirage happen? Very, very interesting. Let's read through this and then I'll try and explain it as best I can. Um, okay, so figure 4 shows a mirage. Notice that there appears to be a reflection of a vehicle in the road. So here's a vehicle, and there appears to be a bit of a reflection over here. Down here, there appears to be a bit of a reflection. Um, the air just above the road is hotter than the air higher up, and light travels faster in hot air. Very interesting. I want you to highlight or underline this word. So light rays from the vehicle that travel upwards towards the road, are bent upwards by the hot air. Your brain assumes that these rays traveled in a straight line, so the rays look as if they have reflected of a smooth surface. Okay, I'll explain what this means in a minute. Let's look at this question over here. Before reading about mirages, too late. Ask a what or how question as you read. Write the answer in your question to your question below. I'm going to ask, what is a mirage? And the answer to that is, it is an image. Oopsie, there's an A. There's an A somewhere. It's an image of a distant object caused by refraction of light. Sorry about the horrible handwriting. It's just really hard to write with these. Um, so this is the pen that comes with my Surface laptop, and it's very good, but I don't know, just it has its challenges. Okay, back to mirages. So why do they happen? Let me explain it in the simplest way I could possibly explain it. Okay, so here is the vehicle. So let's draw a car. Here is the car, and it's traveling in the desert, in the hot desert. And here's the front lights. Um, and here we go. Okay, and over here is the road, and you are observing. You're the observer. Now you are standing over here, and you are observing from far away. You're a bit tired. You're sitting on the side of the road, and you're going, "Oh, when are people coming to rescue me?" But you look at that and you crack a smile because you think, yay, I can see what looks like water in the distance. Well, you should be happy that the car's coming anyway. The point is, you look and you see what looks like a mirage. Now, why does that happen? Let's have a look. Let's zoom in on this part here. So I'm going to zoom in now. What happens is the following. We have the road, which is very, 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 very hot. Should I add another very in there? Very, 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 very hot. Okay, so the road is very hot, which means the air above the road is going to be very hot. So here's what I'm going to do. I'm going to say this is very hot. I'm going to draw in a red. Oh, you know what? I've got a better idea. I'm going to use highlighter. Oh yeah, that's beautiful. So the air is very hot just above the road. But then on top of that, it's going to be less hot. So it's going to be slightly cooler, but still hot. And then above that, it's going to be warm, but it's going to be not as hot. And then it's going to be just kind of lukewarm. Okay, we'll stop there. Now, what happens to light? What happens to the reflection of the car? The light hits the car, okay, because that's how we see things, remember from lesson one. Light hits an object and then reflects back into our eyes. Now, I want you to imagine light's hitting the object, so light's hitting the car, and then it's reflecting back into our eyes, but it's not really. What happens is it goes this way, and then it bends outwards, because remember what I said, slow to fast, bends outwards. Now, light going from cold air into hot air. Remember the particles in hot air are further apart, which means it's going to be less particles. It's going to face less particles, or it's not as dense. So therefore it's going to speed up. So when light's going from cold air to hot air, it's going to speed up. And so this way it's going to speed up, so it's going to bend outwards. Oh, some of you have figured out already what's going to happen. And then it goes to hotter air, so it's going to bend even more outwards. And then it goes even hotter air, so it's going to bend even more outwards. Well, guess what now? Now it's going almost to a straight line, and it's traveling all the way there. Well, who's standing there? That's you right there. And that's what you see. And you're going, yay, I see that. That looks like water. And that's how a mirage forms. And you get to see the reflection of the car. So in short, as light is traveling through the different levels of heat, or different levels of hot air, it bends outwards, outwards, outwards until it bends all the way horizontal and gets to your eyes. Okay? And that's how that happens. Okay, let's have a look here. There's also some questions down here we can answer. Identify a material's what is a measure of how much a ray of light bends when it enters the material from the air. A material's what? A material's refractive index or index of refraction. of refraction. Oopsie daisy. Index of refraction. Okay. Um, Now question 1b. Predict if glass prism were in a medium with the same index of refraction, would it separate white light into different colors, and explain? Remember, in order for light to bend and separate, it has to go from an area of slow to fast, fast to slow, and then slow to fast. And so therefore, if it's not going to experience that change in velocity, then the different frequencies of light are not going to separate. So the simple answer to that is no, because it's not going to experience different velocity. It's not going to bend. Um, it's not going to refract as it enters and exits the prism. No, it's not going to bend. I'm going to write that here because it keeps coming up with those prompts. Bend when it enters or leaves the prism. Okay. And how does light interact with matter? How does light interact with matter? Well, that is very interesting. What we have seen so far, in lesson 1, we've seen reflection. So light reflects off matter. So either it reflects in a regular way, which is why a lot of people would think that mirages look like water puddles, because light reflects off water in a regular fashion. So therefore, they think it's water. Um, so it can either reflect in a regular way or it can reflect in a diffused way, which is what happens when you look at yourself in a wall. You can't really see your image because it diffuses your image. So it can either reflect or it can refract. If it goes through an object, that means it's going to either bend or go through. So it's going to reflect, it's going to refract, or it's going to be absorbed, depending if the object is really, really dark or like a black hole, then it's going to be absorbed. So those are the three options. So it's going to reflect, it's going to refract, or it's going to be absorbed. Okay, and if you can come up with some examples here, that would be great, but I'll leave that up to you. Moving on, what determines the type of image formed by a lens? Very interesting. The type of image formed by a lens depends on the shape of the lens and the position of the object. So two things, the shape of the lens and the position of the object. And I'm sure you've all had the chance to play with these magnifying lenses. We've got them in the lab, but if you haven't, please talk to me. I will give you one to play with. A concave lens is thinner at the center than at the edges. So this is what it looks like. At the center, it's very, very thin compared to the edges. Okay? When light rays traveling parallel to the optical axis, this is called the optical axis, yeah? Through a concave lens, they bend away from the optical axis and never meet again. A concave lens can produce only virtual images. Only virtual images. So that's the first thing I want you to know. If what? Only virtual images. Because parallel light rays passing through the lens never meet. Okay? So look at the book on the right. Notice that the words seen through the lens appear smaller than the words outside the lens. So over here the words appear to be big. Over here the words appear to be small. Okay? The words seen through the lens are virtual images. Okay? Virtual images. A concave lens always produces a virtual image that is upright. Upright means it's standing in the same position, the same direction as the object, and smaller than the object. So as far as concave lenses are concerned, concave lens, image. Image is upright, is upright. That means same direction as the object. Image is diminished or smaller. So we're going to say smaller or diminished. Feels like I misspelled that. Um, and of course, it is virtual. Virtual image. Okay. And the reason it's a virtual image is because those small letters don't actually exist. So those small words don't actually exist. There's no small words. If you look at the page, the words are big, right? But it appears small because what happens is your brain connects those dots. So basically just makes those connections from where the rays have come from. The rays have come from here, but your brain thinks the rays have come from somewhere here because of the lens. And so rather than seeing the rays come from here, you've seen them. Your brain is tricked into thinking that they've come from here, and so the image forms somewhere around here. But it's a virtual image. It's only in your head, and yeah, so it's virtual. It's not real. Okay. Um, and we have an application question here. Extend the two lines. So let's do that. Extend two lines and see if we can draw the image. So it's that's going to be very tricky using this pen. So I'm just going to try. Okay, so that's more or less what I think it's going to look like. More or less. Except it's not going to cross the line. It's not going to cross the line. So I can't get it, but more or less that. So it's going to be diminished. It's going to be upright, and it's going to be not real. It's not going to be virtual. Let's look at convex lenses. Those, in my opinion, are more interesting because those are the ones used for magnifying, and those are the ones used essentially in like telescopes and such, and they're quite interesting. Right, so with convex lens is thicker in the center, so it's thicker over here than at the edges. Um, as light rays parallel to the optical axis pass through a convex lens, they are bent towards the center of the lens. The rays meet at the focal point of the lens and continue to travel beyond. The more curved the lens is, then it means that it refracts light more. And the convex lens acts like a concave mirror in a way because it focuses rays of light. So an object's position relative to the focal point determines whether the convex lens is going to form real or virtual images. If it's going to focus light, then it's going to be real images. We know that from mirrors. If the light rays actually converge onto a point, then that means it's going to form real images. If they don't, and it's just imaginary light rays, then it's going to be virtual. So let's have a look. So depending on where the object is placed, beyond the focal point or between the focal point and the lens, then we can determine whether it's going to be a virtual image or a real image. So a virtual image, remember, is not actually formed by the convergence of light rays. It is formed by the predicted or the anticipated convergence of light rays. So if you look over here, those are all virtual images because the light rays don't actually come back here. They just continue moving. But your brain forms that. Whereas over here, this is going to be a real image. Okay, quite so, because that is a real ray that's gone inside and formed that image. Okay, whereas that is going to be a virtual image. I can tell you right now because those light rays, they don't exist. That doesn't exist. That's just your brain prediction. Okay, that is virtual and that is real. Just off the get-go. Let's go back to reading. When an object is between the lens and the focal point, the refracted rays form a virtual image. The image forms on the same side of the lens as the object and is larger than the object. If the object is outside the focal point, that means beyond the focal point, the refracted rays form a real image on the other side of the lens The real image can be smaller, larger, or the same size. So it can be either smaller, it can be larger, or it can be the same size as the object. The diagram in figure 7 shows how a convex lens forms a real and virtual image. Very interesting. So if the object is over here, this is the object, then the image can actually form behind the object and be upright, but it'll be virtual. Whereas if the object is beyond the focal point, then the image can be over here and it would be, well, depends on where it is. If it's over here, then it might be larger. Whereas if it's over here, then it might be the same size, and so on and so forth. So then we were asked afterwards to list some uses for a convex lens. And some uses for convex lenses is the most obvious one I can think of, the one we have in the lab, is magnifying glass. We also have, what else do we have? We have telescopes. Telescopes are amazing. Microscopes have them as well. We have those in the lab. Microscopes, telescopes, microscopes, and telescopes. Periscopes, like the one we looked at in the first lesson, you know, with the submarines, sorry, and cameras. That's the obvious one, and I'm sure there are others, many others. Okay, let's move on. Ooh, what do we have here? So this looks like the video I showed you in the classroom. It's very interesting. I like that. Interpret photos. These photos show parallel rays of light passing through a convex lens and a concave lens. Why do you suppose a convex lens is called a converging lens and a concave lens is called a diverging lens? Well, that's where your vocabulary skills comes into play. Converging. Converging means they are coming closer together. Converging, okay? Diverging means they are going further apart. Diverging. Further apart. Diverging. Don't divert away from the topic. It means don't go further away from what we're talking about. Let's converge onto a conclusion. Let's come together onto and focus onto something. Right, so let's have a look. Now, knowing that converging means coming together, that explains why that's called a converging lens. Okay, so that is a converging lens because it converges light. So basically, they come together. So converging because it brings light rays together. What a beautiful thought. Brings them together. You know, I know some people in the classroom that are like that. They act like converging lenses, bringing people together. Unfortunately, I also know some diverging lenses in the classroom. We won't talk about that. Well, diverging lens obviously is one where that separates the light rays. Diverging lenses, diverging lenses. Diverging means, I'm so sorry about my handwriting. This is horrible. Writing on glass with this stylus pen that refuses to work half the time, and I have to keep turning it. Oh my goodness. All right. Diverging means separating. Okay. Although I have to say it's easier when the text is bigger. So if I say there's still a delay and it's not working 100%, but it's okay. Let's have a look. Question 2 says review. Complete the lenses and mirrors table. Use the table to answer question 3. Okay, concave mirror, virtual, real, or both? Both for a concave mirror. Depends on where the object is relative to the focal point. If it's beyond the focal point, it's going to form a real image. If it's closer, than the focal point, it's going to form a virtual image. But is the image going to be upright, inverted, or both types of images? Well, it's going to be for a concave mirror, it's going to be, where's the concave mirror? Here we are. Always upright, okay? Always virtual. So sorry, we're talking about the orientation. So it's going to be upright. Convex mirrors. With convex mirrors, they form both. Wait a minute. Oh, we're talking about mirrors. Oops, we're talking about mirrors. We're not talking about lenses. With a concave mirror, so that's that type of mirror, that forms the type of image that's going to be real, and if it's closer than the focal point, remember we did this in lesson 1, we did this in the lab, if it's closer than the focal point, it's going to be enlarged, and it's going to be upright, but if it's going to be further away from the focal point, it's going to be inverted, so it's going to be both. That's mirrors. Sorry, I thought it was talking about lenses. Okay, what about convex mirror? Convex mirror is always going to form a virtual image. A virtual image. Oh, just be careful when you're reading the question, sorry. So a convex mirror is this guy here. I wasn't expecting any questions on lesson 1, to be honest. Um, so obviously a convex mirror is always going to have a diminished virtual image inside it. It's the kind of mirror that's used on the corner of the street, and it helps drivers see around the corner. The image is always diminished. It's always going to be smaller. It's always going to be virtual, which means it's behind the mirror. It doesn't really exist. Okay, um, concave lens. Now back to our topic. A concave lens is a virtual, forms a virtual image, while a convex lens forms both. A concave lens will form an upright image. It's virtual, it's upright, and virtual. What else did we say? Virtual, virtual upright. Was there another point we mentioned? Oh, diminished, of course, yeah. Um, Convex lenses, on the other hand, that's going to be both virtual and real, depends on where the object is relative to the focal point. So if it's beyond the focal point, then it's going to form a real image that's going to be inverted, and it's going to be either same size, smaller, or bigger. But if it's before the focal point, what I mean by that, if it's between the focal point and the lens, then it's going to form an image that's going to be virtual, okay? And usually bigger. Yeah, so there we go. But that's going to be upright. Yeah, it's going to be upright, isn't it? Oops, both. No, sorry, it's going to be upright. It's going to be, let's think about this for a second. It's going to be upright if it's a virtual image. But if it was a real image, then it's going to be upside down. If it's a real image, let's have a look. Let's go back. Let's go back. Here we go. If it's a real image, then it's going to be upside down. Whereas if it's a virtual image, it's upright. Yeah, I was right. So it's going to be both. Oh, it's a bit tricky that. Um, okay. And the last one is a bit of a challenge. Suppose a convex lens and a concave lens. Oh no, oh sorry, we have number 3. Summarize the convex lens acts like a what mirror? Well, it acts like a concave mirror, doesn't it? Look at what we have here. A convex lens acts like a concave mirror. See, they share Both. A concave lens, a convex lens acts like a concave mirror, while a concave lens acts like a convex mirror. Those two are very similar. Convex mirror. Very interesting. Suppose a convex lens and a concave mirror are underwater. Compared to the way they work in the air, which one do you expect will be more affected by the water and why? Okay, back to the lesson. Sorry about that. Suppose a convex lens and a concave mirror are underwater. Compared to the way they work in the air, which one do you expect would be more affected by the water and why? Well, think about it for a second. The lens, okay, the light doesn't bend as much when it travels from water into the lens as when it travels from the air into the lens. So the medium, um, a mirror is in, doesn't it really affect the way it works? Whereas the lens, it would be affected. Um, so I think that's the main point I would talk about is that um, the lens would be affected by the medium it's in because light wouldn't bend as much when it travels from the water into the lens. Yeah, so how do we word that? Which one would be affected the most by water? The lens. Um, oops, let's go back. Yeah, probably need a new stylus pen. The lens because the lens because it experiences um, oh, and refracting at different mediums. I wonder if I write slower. Okay. Um, Define, let's look at these answers here. Define a what is a curved piece of glass or other transparent material that refracts light. So there's two types of them, uh, convex and concave. A what is a curved piece of glass? A lens. A lens. Compare and contrast. Describe the shapes of a concave lens and a convex lens. Basically, one is thin in the middle, the other one is thick in the middle. So I'm just going to draw them, really. That's convex. Oops. And this here is a concave. Make a generalization. Use figure 7 to explain how you can tell whether a convex lens will produce a real or virtual image. Okay. Allahu Akbar, Allahu Akbar. So here is the focal point, which is the point at which rays focus. I've got to go to Maghrib prayer in a minute. And here is the convex lens, so we better finish this. Here's the object. If I put an object over here, if it's before the focal point, then it's going to form a real image behind the lens. But if I put the object over here, then it's going to form a virtual image, and it's going to be on this side of the lens. So my generalization is going to look like this. If the object, why isn't this working now? If the object is between the focal point and the lens, then it's going to be a virtual image, and if it's going to be beyond the focal point, then it's going to be a real image. Um, yeah. Okay, moving on because I really gotta go pray. Write the letters of the correct answers on the line at the left. A mirage forms when, very interesting, a mirage forms when regular reflection occurs, light rays are bent by water in the air, light passes into mediums with greater density, no, not greater density, light refracts as it moves from hot air near the ground to cooler air above the ground. That makes sense. So, and then it sort of bends back out and about, so it's D. 2. As rainbows formed, light refracts and forms a virtual image, refracts and forms a real image, reflects as from a plane mirror, refracts and reflects, refracts and reflects. That is going to be D again. It's going to refract and it's going to reflect, as we saw with the rainbow droplet. The type of image formed by a lens is determined by the index of refraction of the object, the brightness of the light passing through the object is determined by two things. Remember, two things. The shape of the lens and the position of the object. And if you remember, that is actually in the notes, right? Is it here? Depends on the shape of the lens and the position of the object. Okay, and number 4, the type of image formed by a convex lens is determined by the object's position relative to the focal point. Okay, because remember we said if it's beyond the focal point, then it's going to be a real image. If it's between the focal point and the lens, it's going to be a virtual image. In the statement, if the statement is true, write true. If the statement is false, change the underlying word or words to make the statement true. When white light enters a prism, each wavelength is reflected by a different amount. What do you think? True. Is it? Reflected? Wait. False. And it's going to be refracted. Refracted by different amounts. Okay, number 6 says a lens is curved, piece of glass or other opaque material. Opaque? Ooh. True again? Nope. False. Transparent. The faster light travels through a medium, the lower is the medium's index of refraction. Now that is actually true. Parallel light rays passing through a concave lens always meet. Concave lens. Always meet. Never. Oops. Okay. I guess that's the end of the lesson. Subhanallah. Sometimes this happens. You know what? It's time for me to go and pray. Assalamu alaikum. Thank you so much. It's a bit of a long lesson today, but remember, it's a summary of a week and a bit worth of lessons. Okay, take care. See you soon.